Kyle, are you ready as we ever going to be?
I guess so. I'm gonna turn video off if everyone else is.
Yeah, I'm trying to save bandwidth.
Yeah, likewise.
Turn it on for the beginning.
Okay, yeah, I'll say hello.
Oh, Greg McFarland. Look at that.
Yeah, it's me.
Well, hello.
I'm very
Greg.
impressed with Kyle's diploma wall. Rick, you've got a good bookcase. I don't know if you there are now Twitter accounts that rate people's bookcases on Zoom meetings because
Really?
yeah,
That's sort of sad. I don't know. Maybe I should just put the bookcase up there then. And
Well, really is what you should just get a virtual background that
Yeah, it's like the Library of Congress back there.
Oh, that's right. Actually, you can do that, can't you? Isn't there some way you can?
yeah, on a Mac you have
choose
to have a
virtual
quad core
background.
processor,
Yeah.
which is kind of a disappointment. But maybe you have one.
Say, yeah, baby. Except that it makes you look funky.
It does
I'm
make you look a little weird.
Yeah, I'm done with that.
everybody will start as soon as the participant list stops going up in just a minute too.
Elizabeth, do you have any idea how many people were on this on Wednesday?
I think about 60 with 80 people.
Oh, geez, really?
Yeah.
There were that many people?
And there'll be a lot more that watch it afterwards too.
How are they going to watch it afterwards?
YouTube.
It's recording.
You can't do that.
Of course,
Did we agree to that?
Recording all this at the beginning is probably going to be great for everyone who's rewatching. Hello, everyone.
It's okay. I can cut it short.
Hi, Kyle.
I can edit. All right. Why don't you go ahead and start, Rick?
All right. Well, welcome, everyone. As you can hopefully see on the screen, we're here for day 2 of Machine Learning 101 for travel analysis. And let's see if I can get my screen to advance. Today we have 3 case studies to talk about. Kyle and I are going to talk for about 20 minutes each on imputing income and a hopeless mode choice experiment. And then Massam, who's a real master of all this stuff, is going to talk about pattern recognition from truck GPS tracking data. So we saved the best for last. Before we get started and I turn this over to Kyle, a couple of people asked on Tuesday when we did this first, or Wednesday, why there are negative values for the ratio of transit to auto travel times, and I didn't know. So what I know now is that this is why you don't just borrow slides from somebody else. So in the data set, they're coded as negative if we had to impute one or more of them. But when we read it in and we actually did our analyses, we did an absolute value. So that's why. Otherwise, I went through last night and I convinced myself it wouldn't work. At any rate, without further ado, Kyle, I think it's over to you. So
all right.
Take it away.
Okay. Hey, everyone. So as Rick mentioned, I'm going to talk about some work I did back in, I don't know, maybe 2017. But this makes for a great kind of intro into, what's a basic application for something that you could use machine learning for. So it shouldn't take too long. It's pretty basic, but hopefully it'll be valuable. So an overview of the problem, common problem, we had a household survey and many of the households did not report income data, roughly 50% of the samples. Logistic regression did poorly, as did early attempts for machine learning. and we came back and added parcel value. And when we did that, the logistic regression was still pretty bad, but the machine learning model was much improved. So in addition to reviewing kind of the details of that, we'll also kind of retouch some of the decision tree topics that Rick covered on Tuesday. All right, so the problem. Again, so that chart on the right, so those are income ranges or bins. And you can see that the 997 and 998 are the unknowns, and it's roughly 50%. So we need to make an educated guess. And to do that, we're going to use the other attributes of the household. So I took two approaches, ordinal logistic regression. That's not really the focus of this presentation, but I'll just be presenting it as a point of reference. And then, of course, a decision tree approach. So why decision trees? Easy data prep, well, easier data prep. So decision trees are robust to outliers. And if you think about it from Tuesday, you ask questions. And if you ask the question, is the household, the size, is the household size greater than 3? Well, if you have some household out there with 4 or another household with 20 people in it, the answer is still the same. So that kind of builds in robustness to outliers. And for similar reasons, decision trees don't require feature normalization. And that's looking at neural nets. Decision trees are also easy to conceptualize. They're easier to audit. The feature importance that comes out is actually directly used by the algorithm to make its predictions. And they are excellent for classification problems. All right, so downsides. They take longer to train on enormous data sets, and they're not the best choice for regression problems, or prediction of continuous variables. Luckily, in our case, none of these apply. Household surveys are a tiny data set, and we're classifying income groups, not an actual value for income. So here's the decision tree intro or review. On the right, decision trees work kind of like a game of 20 questions. So if you're trying to determine if someone's retired, you would ask a series of questions to make an educated guess. So you might say, are you over 65? And if no, you're probably not retired. If you are over 65, then you might ask, well, are you over 75? And if no, you might be retired, but if you're over 75, you probably are retired. Bootstrapping or bagging again, that is resampling your data. So, you have this original data column and you basically redraw from that and you train your decision trees on each one of those to try to make it robust to specific noise in the surveys that you got in your original data. Random forests or suffrage for DTs. So random forests take bagging, but each decision tree gets to make a random selection of what features they're going to ask questions about, and then they vote at the end. And that kind of aggregate voting makes the predicted choice a lot more robust and expandable to training data, or to test data and unseen data points. So in this case, we have our starting decision tree, but then we might come up with another one, which is, asking about, do you collect Social Security benefits? And so those two might give us two decent guesses that would then vote on the probably or probably not. Boosting, instead of putting them side by side and voting, we actually run them in sequence. So we have our first decision tree, and from our training data, we'll know which ones it got wrong. And then we'll train our follow-up decision tree on those. There is some advanced weighting of those erroneous predictions, but I'm going to kind of hand wave that away for now. And then finally, talk about some hyperparameters. So in rounds, this is for boosting. Basically, this is saying how many decision trees can I build in sequence. So Rick talked about the trade-offs between bias and variance, or overfitting and underfitting. So the more decision trees that you allow to follow up, obviously you can fit any data. If you have 100 trees in sequence or 1,000 trees, you can fit any noise that you see. If you don't have, but you won't extrapolate well or predict on unseen data. If you have too few, then it's kind of like the linear regression that Rick showed, where you actually you don't have enough variance to accurately capture the nonlinear patterns in your data. So ETA is another one for boosting only. That's kind of learning rate. So in neural nets, you talk about lambdas, but when you're boosting, this controls the amount of weight shrinkage. And again, I'm going to hand wave that away, but you can read up more on ETA and learning rates for decision trees. An easier one to understand is max depth. How many questions can each decision tree ask? Is it a game of 20 questions or 4 questions or 100? Lambda is L2 regularization. So this penalizes large model coefficients, and this is to help prevent overfitting. I can't remember, I might have said lambda earlier when I talked about learning rate. That's alpha. And of course, there's many, many more hyperparameters. So how do they learn? Well, I'm not going to cover that here, but at a really high level, information gain is key. Guinea impurity is key. Rick mentioned gradient descent. And the algorithm that I'm actually going to cover is called XGBoost. And rather than a basic gradient descent, it uses the Newton's method. And the question there as well, why calculate one derivative when you can do 2? And Newton's method uses those 2 data points to help shoot your gradient descent in a more optimized pattern towards local minima. And a couple slides in this slide deck are kind of meant for when we release the slides for you to click the links and go back and read and follow up. And those links are provided here. All right, so we've kind of covered, or we've at least retouched what Rick went into more depth on from Tuesday. So back to our actual problem. And we need to guess incomes for half of those households. And to start, we only had the features in the household survey, things like size and autos and all the things that we're all familiar with. So lots of cleaning, and that actually included some minor imputation. So, households fail to report lots of things. But if you're only missing 10%, like let's say, 10% of your households failed to tell you about how many autos they owned. Well, when you're missing such a small fraction, you can use much simpler imputation methods. For example, you can just take the households that cross-classify them by, some other attributes, and then just take the most common auto ownership to make a decent guess. You can get more advanced, but for some of them, you don't have to. And then, as I mentioned, the initial logistic regression and decision tree did poorly. So, bright idea. Let's get the parcel value information for every household. Simply because a big house probably means more income. Well, as it turns out, as with most ideas, this isn't necessarily novel. It took a long time to collect this data for multiple counties. Each county had, different parcel formats. It took a long time to clean it and a long time to combine it. And after I was about a day or 2 in, the person I was working with said, "By the way, we've tried this before. It doesn't help," which I guess, but maybe because I was 2 days in already, or the obstinance of youth. I don't know, but I kept going and finished it up. So, what was the impact on the logistic regression? It didn't help. Here's some results. That highlighted in red, that JV, that's justified value, or basically like market value of the parcel. And you can see its coefficient is small, tiny even, compared to other explanatory variables in the model. The t-stat is fine, but not fantastic. So yeah, it looked like it might be a lot of work for nothing. But the impact on the decision tree was decisive. So these are all the features in the decision tree, and the bar represents the importance, or from Rick's presentation, how useful it was in splitting the data into kind of homogeneous sections to make predictions on. And obviously the parcel value just way outperforms everything else. But there are interesting secondary and tertiary explanatory variables, like, if you own a toll transponder, do you rent your home? How many workers are in your household? Those are all very logical things that that a human being would pick up on to try to help make their decision. And so it's good to see that the decision tree picking up on the same things. So some info on the specific DT that I used. I mentioned extreme gradient boosting. That's the XGBoost model, which is really popular. It won a bunch of Kaggle competitions, and that kind of put it in the limelight. So I used random hyperparameter tuning with threefold cross-validation. That's the withholding a third of your data and then using the 2/3 to train, and then predicting on the 1/3. And in addition, I think this is important to point out, before doing that, I withheld 10% sample from the entire process. So an important point to make is that your final test data set shouldn't be used in any way during training. Cross-validation is not enough, because if you think about it, if you use 10 or 20-fold cross-validation, you are still using that withheld data set to pick your best parameters. So what you really want is to make sure that it's truly robust, is to have an additional set that's withheld that was never used in any way to make your predictions against. So as I mentioned, some detail slides for people to come back and review, but I did want to just show that this is an R, but it's not horribly scary to set this up. A couple lines of code to create the learner, the second block of code to set up the hyperparameters that I want to optimize, and then a couple other steps that I'll let you follow later. But then the last 2 steps was, create a learner and train it. So it's really not, as from Rick's Tuesday presentation, the ML code box is that tiny little black box. It really doesn't require much. The machine takes over and does a lot of the work for you, which is nice. So confusion matrix, Rick presented these, and this is a great way to kind of highlight the linear regression versus the decision tree. So with the logistic regression, basically no matter what you actually were, the model was predicting that you were either in group 5, 7, or 8, with very little predictions made outside. The decision tree, however, you can see is much more diagonal, and is just a better model overall. And when it's this obvious, it was a big win, and we obviously went with XGBoost to do our predictions. Just before I wrap up, there's a bonus example. So back when I was learning how to do XGBoost, I used the Kaggle competition site has an introductory Titanic data set where you predict, who was going to survive. And it's really a step-by-step guide to using it with tons of detail. So it really goes through everything that I did with the data set. And I think this is a great resource for people to use if you want to really get down and dirty. But for our example, and kind of more germane to what we all do for a living, this income imputation is a little simpler and maybe a better fit. Some closing thoughts. A big thing is that decision trees, we actually had a question in the chat on Tuesday, but decision trees can reorder their questions in response to new data. So, the initial decision trees did really poorly, but when we added in the justified value, it didn't just kind of get added into the mix. The DT took a second look and said, wait a minute, this is clearly the most important variable, so I'm going to ask questions about it first, and then use the other ones to kind of differentiate once I'm down into the leaves of my tree. Then those can help me make additional decisions. So again, DTs, they're one of the easiest learners to conceptualize. And I do want to point out, it's not artificial intelligence, but it is incredibly powerful. And that's all for me. Thank you very much. Rick, I can toss it to you next. Oh, well, actually, I guess I should stop and ask, if there are any questions.
Kyle, you did have some questions about, can we find the signs of a feature's importance, positive or negative?
So the signs of a feature's importance. I think what I would say is that obviously makes a lot of sense from like a logistic regression. But here, when you think about asking questions, you would ask something like, are you above 3-person household or are you below 3-person household? So within the model, there, the sign doesn't really come into play. However, we mentioned this a little bit, and I think it was David mentioned in the chat, there's explainable AI. And, you could take the model that I estimated and synthesize data, changing, certain distributions of things like size. So for instance, if we just take size, you could increase everyone's size, decrease everyone's size, and try to kind of intuit how size influences the predictions that it makes, to sort of get it, well, do larger households have more income? You would have to kind of tease that out through some post-processing and some testing.
Kyle, you had another question in the chat box. Is it possible that the model is overfitting?
It's always possible. So I'll go back to make it a little bit clearer. This confusion matrix, this is a randomly withheld. These are predictions made on a randomly withheld 10%. I think it was 10%. Of the samples. So these confusion matrices, the fit back to the estimation data or the training data is much tighter. It's probably, for the XGBoost, it's probably almost all along the diagonal. But by withholding, by doing cross-validation, by implementing things like, let me go back to this slide. So for instance, my max depth, I only allow each tree to ask between 1 and 3 questions. That's very conservative. Now I do allow between 100 and 200 of those small trees to go in sequence, but I have L2 regularization in place and ETA in place to help me. So it's always possible, but I think the key is that by doing all those things to keep the model from overfitting, and then confirming that by predicting on a true test set, like I'm showing here, I think we can be relatively confident that we have not overfit the data. Any others? Okay.
Yep, Kyle, there was a few other questions.
Sure.
One from Rosella. How confident can you be that applying the same model to a different case study, it will behave in the same way? And then I'll add in David's question too. Experience shows that boosting seems to be more resistant to overfitting than most other machine learning methods, which I guess is not a question, it's a comment on the previous question.
That's right. And particularly because, you know, I definitely did some hand waving on the weighting of the residuals and the shrinkage methods applied. But boosting is, it's really popular for lots of good reasons. So it is, it's a good method. Anything can be overfit, but it's pretty robust to that. So to Rosella's, so it's a good question. Work that I did with Rick and Mossam up in Canada, we were doing a mode choice model and we had the same thought. And so what we wanted to do is start combining surveys from lots of different places, you know, add New York, just basically add a bunch of different stuff into the observed data. So for instance, I wouldn't say that I have extreme confidence that this model trained on the data that it was trained on, could I take it to another state that looks very different and expect it to perform perfectly? I would expect it to do decent, but as well, I'm not sure. So what you would want to do is try to aggregate data. So combine household surveys. And basically that's so the learner can see more observations. And, you could even, it's a little bit cheating, but you could even put as explanatory variables the state that each sample is in, and the decision tree would ask about that too. So I think the key to making sure that it's transferable is to try to add as much data and give it as many different, as much variance in your observed data set as possible. Elizabeth, feel free to keep them coming.
Rosella had another question about what the machine learning model could tell you about how to use the parcel information in the econometric model. If there was a transformation or an interaction in some way.
Rosella always asks good questions. I don't know. Perhaps there is some kind of transformation that would make it more weighty or more likely to be picked up on, but I certainly didn't attempt it and couldn't really speak to it with any kind of authority. Perhaps. I certainly can't take the feature importance graph. So I know it's important, but that doesn't tell me, that doesn't give me or outline some technique that I should apply to the logistic regression.
All right, that's it.
Okay. All right, thank you guys very much. Rick, your turn.
All right, well, I'm going to be at a higher level a little bit with my problem on mode choice, and I unwisely chose inner city mode choice as my first problem to tackle with this. In fact, we were pretty content to go after this with just regular logit models of discrete choice. And so we started out with 4 data sets. 2 of them, I don't have permission to show on a screen here, but 2 of them that we used was the NHTS from 2002, about 45,000 observations of intercity trips. And there's also the Travel Survey of Residents of Canada, which had exposure to on a project recently with Mossam and a little bit of Kyle, where we had about 168,000 observations. When you scale them down by throwing ones out that had missing or illogical values for mode, you get a pretty decent sized sample. And a lot of these have a lot of the same attributes. So we got to looking around and trying to find different sources of information that we could possibly fuse together into a single database to do model estimation with. Now, of course, if most of you that are into mode choice already know what my problem is that it is so over dominated by auto. 90% of the observations, and for the 2 data sets that I don't show you here, same sort of problem. And so if you just get auto right, you can afford to be wrong about everything else. And a lot of times, that's exactly what happens. I unfortunately had a client who was not happy with the idea that we'd be wrong about the non-auto modes and insisted we come up with something that would do a little bit better. So if you follow the literature on this topic, you know that there's a long collection of models over 20 or 30 years with pretty mediocre fits, and a lot of different types of discrete choice models have been, and aggregate models, in all fairness, have been tried, but nothing sort of worked really well when you're looking at the non-auto modes. So this is a perfect case of imbalanced data, which is a curse in machine learning. But we were wanting to take a look at, can machine learning overcome poor sampling design? And we thought, well, yeah, sure, of course it is. It's like magic. So when we started out, we had a logit model that was put together by some people that are pretty smart in this sort of realm. And you can see the percent incorrect predictions when we ran this thing in a multi-agent system. In other words, we have discrete agents that we're running mode choice on, and we're getting discrete outcomes. So we can just do a classification error and come up with the exact number that we're getting wrong. And we sort of arbitrarily wanted to be within 10% on each of these mode shares. And as you see, logit model didn't do great. Random guessing does really well, unless you care about anything other than auto travel. And so this is an example of the confusion matrix we got when we just made a random guess. As you can see down there in the middle of the screen, the accuracy is 0.81 overall. The only problem is that, as you can see here, and this is one of the 20 trials that we ran, that it gets it wrong pretty much for everything else. Unacceptably wrong, worse than the logit model did. And so we thought, well, there's got to be something better we can do. And so we decided, let's build a decision tree and see what comes up. And its accuracy was actually pretty great, 0.94, but it did no better with most of the other modes. One thing it did provide, though, is it provided us a very keen insight into what the breakpoint variables were at the various levels, something that we were having a hard time visualizing when looking at the results of the discrete choice model estimation. And so this model came out and I looked at it and everyone thought about it and thought, wow, yeah, we can see all this stuff making sense. But Rick, we still got to be able to do better. And so we were sitting in one of our favorite restaurants, and we usually have Thursday afternoon get-togethers over chili con queso and margaritas. That's a thing here in New Mexico. And we had this new gal on the team, fresh out of Stanford, and she's sitting there and says, I can build a neural network model in just a couple of days that will outperform this thing. And, you know, there's like half dozen of us around a table, and we're all thinking, oh gosh, you know, it's like, yeah, sure, right. And so eventually there became quite a bet, and she actually did build a neural network. This is her first run through it, and it actually did outperform everything else, and we lost a fairly expensive bottle of really good tequila to her for the efforts. But it did get us thinking about, well, there's got to be ways that we can do this. But of course, everyone we talked to in the ML world said, well, if you have a really hugely imbalanced data set like that, you got to do something about it. And so we looked at all the alternatives out there that we thought, well, maybe we could make sense of this. The first and probably most prevalent piece of advice we got from everyone, and also the least helpful, was that you need to go back and do a better job of surveying. I thought, well, yeah, that's fine. If we can't do that, then they'd want you to go back and do targeted surveys of the underrepresented modes in this case, and fuse them together. And we, of course, in travel demand forecasting, we've got a long history of doing that with our aggregate models, where we would go do a household survey and a transit onboard survey, and then we would do a weighted fusion of them to do our mode choice model estimation. So I thought, well, that's okay. You could reweight them. We tried clustering them in similar classes where we could find similarities. There was one method that seemed to offer a lot of potential call precision recall methods. Someone else worked on that, and then he left before we really got through it, and none of the rest of us really understood it. But we did get bagging and boosting and XG boosting, as Kyle just talked about, and then we were finally overwhelmed with gratitude when SMOTE hit us, because we thought, oh, this is going to fix us, because here's a technique in machine learning that's going to work great for our problem. And it didn't. So then we looked at over and undersampling, and it worked decently. And then we came down to what we call the successive elimination of dominant outcomes, or CEDO. And you've never seen this in the literature before, because we made this up basically. And I'll show you, what happened. Before explaining CEDO, though, I should tell you what happened when we tried all of these different approaches, and that's what you see on the screen here. You see the percent incorrect predictions by mode by each of the methods that we tried. And for some reason, the SMOTE, I could not find the table that had the SMOTE in it, but there is one in it. It falls in about the middle of the pack in terms of performance. And those on the top, in part A there, are where we use the full data set. And in this case, we're looking at the NHTS data set. We used the full data set for our training data. And on the bottom was our best over or under sampling outcome, which varied. It seemed like on decision trees, if we undersampled, we got better results. With the bag trees, it seemed like if we oversampled, the less common outcomes, that work better. And the neural net, it seemed to work better with undersampling the dominant mode of travel. And so you see there over on the right-hand side, the ranking of these methods. So I'll explain the difference between CEDO random and CEDO bag tree shortly. But those two hit the top. They were the least worst of all of these models. Now keep in mind that the shaded green here is the acceptable outcomes, and our client, of course, very unreasonably, or well, maybe reasonably, wanted green all the way down the column. And the numbers in red that you see there are the best performers for each mode. And really the CEDO plus random, it came the closest for us in terms of predictive accuracy for the non-auto modes. Not great, but decent. So we decided to investigate how we could make this CETO thing work a little bit better. And so if you don't have video on, well, even if you do, because I'm not watching video anyway, you have to hold your nose at this one, but let me show you what it is. So we start out with the entire data set, the very full training data set of all observations, and we split it into a training data set, which was, I think, 80% of the observations, and then we had 20% holdout for our testing. And then we calculated the percentage of observations for each response variable in our modes. And then we tested to see if there was a dominant response. And a dominant response was one that was more than 1/2 of the total observations. So really low bar to clear. And we said, if there is a dominant response, we're going to classify that dominant response versus all other. In other words, we're going to do a binary choice model. We just want to classify auto versus the rest of the world. And then, whoops, then if that works with acceptable accuracy, we store that model for that first level. And if it's not acceptable, then the thing reformats the hard drive and the test is over. But if it does work, we store our model and then we eliminate those chosen alternatives. So the first time through this, of course, I'm going to be doing auto versus non-auto. And then I eliminate all the choices for auto that have been made. And I go back and I do this again with the remaining modes. And I say, is there a dominant one? Of course, it's going to be air. So I classify air versus everybody else. And then I go through and I run this thing through again. And then finally I get through on the last time through and I no longer have a dominant response because my remaining modes of other, rail, ship, and bus are reasonably distributed in my population, and I no longer have an imbalanced data set. And so then I stop and I do classify with all response levels, and then we're done. And when I implement this thing in code, let me show you the model first, and I'll come back to the code. So this is an illustration of what the 3-level run through this model might look like. And of course, in each case, the non-dominant mode is what gets fed into the succeeding one. So in this case, you see 3 trees, but the beauty is you can use any 3 models. They don't even have to be the same machine learning models on each level. You can choose the one that works best. We did a bagged tree, bag decision tree for this, which seems to work the best for L1 and L2. And then, as you may have noticed a little earlier, actually, when I get down to the bottom, no model works really well at differentiating between bus, other, rail, and ship because there are so few observations. So actually, if you just randomly guess, instead of using a decision tree on level 3, you get a slightly better outcome. So that's what we did. We've got 2 bag models and a random model. And the way we implement this thing in code is we just load the data sets. We increment the level. So now I'm on level 1. I apply that auto model. Those that choose auto, I append them to my output data set. And then I remove all of them from my prediction data. And then I go through and I increment to level 2, and I go through and I do the same thing. And I keep going until I've exhausted all my levels, which in this case is 3 levels. And we showed this to a peer review panel of machine learning people, and they were kind of like, wow, that's pretty wild that you did that, but I don't really see anything wrong with that. There are no hard and fast rules about how to choose a model in machine learning. And as Kyle was mentioning in the answers to his questions from the audience, we went to a lot of trouble when we were doing this to minimize the test MSE and to come up with the lowest error, as you saw, for these non-dominant modes. Anyway, the final modeling system that we're using actually in production is we go through certain error definition, we run through an economic forecasting model, we do long distance journeys, we do a primary destination choice, and then we run 3 mode choice models. And then we poll the results of the 3 of them. And as you can see, we have the neural net, we have a logit-based mode choice model, and we have the CETO with the random tails that I just told you about. And about 70% of the time, 2 of those 3 mode choice models agree. And so we take that. If all 3 of them are different, which does happen, we just go with the logit model and we keep on going. At any rate, we feed that into our network analyses. And of course, we go through this mode choice loop. Each one of these boxes is a multi-agent model, so we're doing this on a discrete level. So one thing that was important for us, because one of the big criticisms of the reviewers was that, well, your machine learning model probably does a decent job at the training data, but if you feed it data that weren't in the training data, the logit model is going to behave really nicely, and your machine learners are going to go into orbit around Neptune. Well, it turns out that it's not really the case. We fed some data through, for example, like unemployed people with the lowest income categories that are flying the longest distance by air. I mean, going the longest distance that we had for air passengers, which none of the low income people did in a survey, but we did a bunch of that, and all these different edge cases that we could contrive out of the data. And pretty much most of the time, logit model and the neural models all kind of moved in the same different direction. And they didn't come up with the same answer, but the degree to which these models don't agree is as useful to me, anyway, as which one of them does agree with one another. So here's my takeaways from it. After spending a lot of time and being on a team where I was the dumbest person about machine learning, and by their estimation still am, there's no amount of machine learning brilliance that can overcome poor data. Our over and under sampling, which seems to be a time-honored and preferred method in a lot of machine learning applications, didn't work out as well as everyone told us it would. The data themselves have too many unincluded attributes, obviously. There is something that must differentiate the decision between bus, rail, other, and ship, but we couldn't find it in the data that we had available. The one things that we liked about the CETO model is that you can update this model with new data in just a matter of minutes, and you can save it out on the model cache, and it's right there and ready to go. You don't have any new model estimation to do. We have a little bit of code that looks at the old outcome versus the new one to make sure that the new model that you're shuffling into place doesn't have wildly divergent estimates from its predecessor. But the beauty is it incorporates new data just amazingly well and very quickly. You can use weighting and replication to reshape the input data. So if someone comes along, as they always do, and they say, well, what if we really dramatically improve this and we do that and everything, or I want to do an SP survey and I want to add Hyperloop, what can I do? It seems like it's a whole lot more amenable to going back and filling this. And the last thing is, when we explain this to our taskmasters, they totally understood what was going on. And we were clear with them. I said, well, really it is a black box, and we eventually want to get rid of the logit model and just only use the black box. And it's hard to understand what's going in some black boxes, like the neural network. And the boss kind of smiled and he says, Rick, truth be known, we know that you don't understand the multi-dimensional space of a logit model utility expression any better than an average person. And so really they're both black boxes as far as we're concerned. So I started thinking about that, and where can and how can we use these models to fill gaps that we can't already. We're not there. We still have to go back and do the surveys to fill these gaps, but at least we know what we're looking for. And we may not have gotten the insight we got without machine learning. And that's kind of it. Kyle, have you been watching the chat box for questions?
Yeah, a couple I have answered. One was
Cool.
from Rosella, and she said, what does it mean?
Rosella?
I know, right? She's full of good ones.
She's really getting us.
She said, what does it mean that 2 or 3 of the models agree? Is it that they give the same choice of a given observation?
That's right. So you have an agent, and all those attributes, you run it through, and each of those models is going to give you a prediction of the mode chosen for that agent. And 2 out of the 3 agree, or if all 3 agree, which is pretty rare, but if 2 out of the 3 agree, which is not rare, we go with that majority vote, so to speak.
So Billy Charlton asked, in short, why you chose an ensemble approach of those 3 models rather than just go with the CETO plus random, since it was the best in your training data.
Because we don't have enough experience with this thing, using it in prediction yet, to feel totally comfortable. And so we wanted to continue with 3 of the most promising approaches, or the more traditional logit model, as well as the 2 most promising machine learners, just so we could look and see how often they agree with one another over a wide range of things. Our goal is to just go with one of them. We just don't know which one yet.
So I actually got his question wrong. He's clarified. Sorry, Billy. He said, when the 3 models have different answers, why did you pick the logit model, that answer?
Oh, that is a user-defined parameter. You can give it the dominant predictor in the control file. We just use logit model just to give, actually, I don't know why we chose that. Probably because it was the least controversial at the time with our review panel. I think now we would probably choose CETO plus random if we we're going to do the skin, but at the time it seemed to be safer to stick with what everybody knew. Bad answer, but that's the reality.
All right, I think I'm going to scroll up and just check to see. Oh, okay. Elizabeth had a question. She said, I'm curious how each model performs within a decision space. Where do they each run wild from each other?
They don't really run wild from one another on anything we've fed it yet. When they disagree, it is always when they're disagreeing about one of the less dominant modes. The biggest space for error is when you get a high income person traveling between 100 and 250 miles by themselves. If you look in the data, it almost looks random as to whether they're going to drive or whether they're going to take rail, and it's probably a function of the rail service. And we have not put in a dummy variable yet to try to determine whether rail was a great option for them. None of these data sets have data available to us down at a level precise enough to make that decision. We could maybe go back and sign a NDA with various data owners if they have point-to-point data, but in these two cases, they never collected that kind of information, so you're kind of stuck with it at a pretty broad geographic level. The one thing we had thought about is building a model only of the Northeast corridor and where rail is much more dominant and see what happens. And we might still do that. We haven't done that yet.
So we had a question about the CETO approach. It says, after you're done with the first round, auto versus non-auto, say you get 100 non-auto answers from that model. Do you feed the 100 to the next round? And what if most of those 100 were misclassified at the first level?
Well, we're running this on a pretty big synthetic population. You wouldn't have a case where you had such a small number of observations, that small of a number of observations surviving to the second round. In fact, there's hundreds of thousands of observations that survive all the way to the third. So,
well, I think just reading the question, generalize it to say like if it was 10% of your samples, like what basically, I think I've already gotten in trouble for reinterpreting one question, but you know, how do misclassification errors from earlier models trickle down into the lower level models? This is a conversation you, Mossam, and I had with the Toronto data.
I don't know that I have a good answer. We haven't spent a lot of time trying to look at misclassification, and we had thought about assigning a probability for that, but we haven't done that yet.
I think if I was going to give a short answer, if the first one gets it wrong, the other ones probably get it wrong too. So
sure.
It's just going to be wrong.
They have no choice because you if they got it wrong on the first model, there's no way to go back to the first model. You're just stuck with the alternatives that are left, and you're going to choose the one that's best.
Okay. All right. I think.
But Kyle, the one thing I will say is that, as you saw earlier, that the first two levels are pretty doggone accurate: auto versus non-auto and air versus non-air. I don't know what would happen if you tried this in an urban setting where we have a lot more labeled choices. Probably isn't. I don't think CETO would even work in an urban area.
Well, it's just thinking. This is kind of off script, but it's similar to approaches that we had talked about for saying, all right, well, like the nested logit model has layers, and the first layer you just try to pick, auto, transit, non-motorized maybe. And so you might build a neural net or a decision tree that does that. And then underneath each one of those is a subsequent model that tries to then further categorize. But so I think the same idea would work, but still, yeah, any errors in the top level models are going to trickle down.
Yeah, they're going to percolate through the model and without recourse.
Yeah.
This was just our attempt to say, well, the reason the logit model goes wrong and everything else goes wrong is that they're trying to minimize an overall error minimization. And if we didn't have imbalanced data, we wouldn't have this problem. But we haven't figured out how to tell a logit model, much less machine learning, just focus on the small representations and focus your accuracy on them. That's why we've had to just successively decompose the problem in CETO. Maybe not a great answer, but It's at
All
least
right.
honest.
That is all the questions.
Okay, good. So, so you and I have really blown our time budget. So without any further ado, Massam, over to you.
Thanks, Rick. Let me just share my screen. So I just want to say that I hate going after Rick. Not because he eats up the
Why?
time budget, but because he does such a fabulous job, it puts a lot of pressure on me. But I'll try and do my best. I also recognize it's a Friday afternoon. People want to get out. So I'll keep the presentation short and hopefully entertaining. A little bit of a story might help just to understand that, and to appreciate that we didn't get into this knowingly. We actually got into this unknowingly. And that sort of resonates with the topic, which is unknown to known, predicting truck GPS commodity using machine learning. So Rick and I have been working up here in Canada for the Ministry of Transportation Ontario, building for them the biggest passenger and commodity and truck model using a whole host of data sets. And because they really liked Rick, they told us in January 2018 that, guys, we have all this significant, like probably 1 billion points of truck GPS data, but we would really like to understand what commodity it's carrying. And, it's completely anonymized. So you have no information about it. But on the other hand, we have this really fantastic commercial vehicle survey of 44,000 trucks that we do every 5 years. And, can you guys do something with it? So like typical consultants who love to get involved in something without actually appreciating the complexity, we jumped up and said, absolutely, this can be done. And by about fall of 2018, we were really scratching our heads saying that how the heck are we going to marry these two things together or crosswalk it together? So as luck would have had it, we were all working, Kyle, myself, and Rick were all working in machine learning feverishly, but from a more traditional standpoint, we were building these travel demand models like the mode choice model, trip distribution, auto ownership, and so on. And I thought, okay, why not just bring over that approach into GPS, into the truck GPS, and how difficult can it be? Well, that was a big mistake, but regardless, the result of that mistake is what I'm going to present to you all today. So the outline of my presentation, I'm going to talk about what I call ML plumbing, which I've shamelessly borrowed from an article that was written by some folks who are working at Twitter. Then I'm going to talk about the problem statement, the motivation, the data, the learner, and some reflections. Actually, let me suppose. So ML plumbing, when you think about, and when you read about a lot of the big data and what Google is doing, what Twitter is doing, what Facebook is doing, they're actually in this scalable big data mining mindset. And you'll see in this graphic that the ML code, which a lot of our discussions have focused on, is actually a really small piece of this mindset. And this ML code is actually surrounded by some significant heavy lifting in terms of how do you configure the model, how do you configure the data, how do you configure the platform, what's the data collection effort, the feature extraction, the data verification, so on and so forth, all the way to the serving infrastructure and finally to the monitoring. And all of these boxes, other than that ML code, are what's known as the plumbing. And this is really the core of any data science project is this plumbing, because that takes up about 80 or 90% of your energy and your time and your budget. Whereas the ML code is actually a very small fraction thanks to a lot of great libraries out there. Now, this is the perfect world. And if you're dealing with Google, Twitter, and so on, this is what they're going to be doing. What did we do was a very ad hoc mindset. Because as I mentioned, we jumped into this with a whole bunch of unknowns. So in terms of configuration, we chose a framework that worked best for a certain type of problem. And what that involved then is that later down the stream, we had to stitch it all together as a patchwork of components. The data collection, unlike when you're doing it in the Facebook and the Twitter world, the data collection here was already a priori. That means the data already existed. We had very little insight or very little influence in what type of data should be collected. It was already presented to us. Feature extraction was implemented within the ML architecture itself, and I will talk about that a little bit. The ML code was implemented using H2O library in R. It was estimated in R. It was implemented in Python. And I'm a big fan of the H2O library, and I know there are a whole host of others, but like if there's anyone who's looking to start in ML, I would recommend starting with the H2O library. There was a whole host of data verification, which we did using Smart. And I know Rick has spoken a little bit about Smart already. I will also introduce it very lightly. And then finally, we looked at the serving infrastructure in terms of a platform to actually display, mine, and share all these ML results. And I unfortunately cannot show you all the platform because I don't have an approval from the client to show the platform, but be assured that this was probably the most sexiest part of this entire project, was that visualization dashboard and so on. And then there were some other boxes that we didn't touch, which is the process management tools, the analysis tools, and the monitoring, simply because we are not looking at a live application of this model. Like it's not like we're getting data in a live Twitter feed or things like that. So, when I'm talking about in all the subsequent slides, you got to please bear in mind that we started with an ad hoc mindset, and like, hindsight is 2020. If I had to go back and redo this, yes, I would follow more of the above, system, which is scalable, but, it was quite a ride just doing the ad hoc. And I think the lessons that I learned doing this are probably far more important than if I had jumped into a framework which is more scalable and more formally defined. So the problem statement, MTO had two problem statements. They first said they wanted to crosswalk the commodity flow patterns from the commercial vehicle survey to the completely anonymized truck GPS data. And then the second problem statement was they wanted to identify the empty truck trip or trips in a given truck tour that you can get from the anonymized GPS data. So I'm only going to focus on problem one, although both problems 1 and 2 were dealt with using the same ML framework. But given the time we have, and I'm only going to talk about one. So motivation, I think we spent about 5-6 months noodling, debating, and arguing about approach 1, which I call the brute force method. And our focus was that why not just Monte Carlo observe commodity flow patterns by broad OD pairs, and broad being, you take all the OD pairs in the CVS data and you map it up to a census subdivision level, which will reduce our dimensionality, and then it will allow us to sample just these commodity patterns and attach it to any GPS truck flow that is moving between these given OD pairs. On paper, that seems like a very easy thing to do, but we soon realized that we would only need a total of 9,889 statistically significant OD distributions, even after we moved it up to the census subdivision level. So that didn't seem a very promising way to go. Then the other challenge with the Monte Carlo technique like that, which is just basic, was that the survey is a subset of of all the OD patterns that the GPS might have. So, where we have 9,889 observed ODs in the survey, the GPS has probably around 40,000. So then what do you do for those other 30,000 OD pairs? You would have to come up with some sort of a synthetic process to map it into those 30,000. So, that didn't seem too appealing either. And then, of course, if you use a simple Monte Carlo technique like that, you cannot capture the relationship between commodity flows and firms because, you're completely ignoring that information. So this was debated around for a while. And come October 2018, I said, okay, let's try to do a machine learner. And the questions in my mind were, why not use a survey to understand the commodity classification and then map it to the GPS route traces? So in the survey, the good part is that it actually is capturing 42 different SCTG2 classes, or 14 broad CFAF, and CFAF stands for the Canadian Freight Analysis Framework categories. So, we could actually map all that information and it just becomes a classification problem. Then once again, in approach 2, by using a machine learner, you can actually generalize the information to the OD pairs where you don't have a survey, right? But where you have a GPS, because then it becomes a matter of applying the model onto the GPS data. And we also firmly believe that, by building a machine, by building this ML, we can actually capture the relationship between commodity flows and firms. We didn't go and mine that explicitly, but just because we have a machine learner built now, it actually allows the client to go and look at those relationships. So after we presented approach 2 to the MTO, there was general excitement that this can be done, and our success on the mode choice and the auto ownership level meant that we knew what we were talking, or at least we were pretending back then. So we moved on to the data. So I'm going to talk a little bit about the data. There were 3 different data sets that we had at our disposal. And now bear in mind, these are already collected and they are pre-existing data sets. The first one is the CVS, which has 44,000 truck surveys conducted every 5 years. It's an intercept-based survey, but it's got a wealth of information on a lot of things that you want to do with it. But specifically for the work at hand, I've listed out the important variables in that survey. The first one was commodity classes. It actually tagged the commodity in a truck into one of the 42 different SCTG2 classes, or an equivalent CFAF group. It did have information on the number of stops in a truck tour, including the trip origin, the commodity origin, the previous stop, and so on. It had the latitude and the longitude of each stop, and that was tagged to a CSD, but you could also get the lat long, actual lat long. And it had the weekend versus the weekday flag, and it had a tour length. Now the tour length was actually imputed in many cases by using the number of stops in a tour, and they've done a whole bunch of QA/QC, and the tour lengths, what we found, they varied between 5 kilometers to about 7,500. In terms of firms, we had a firm data set for the entire province of about 390,000 firms, and each firm had the CSD it belonged to, it had the lat long, it had the NAICS and the employment size, which was a range, and it had the number of employees in that firm, which were imputed as being a midpoint in that range. And finally, we had the economic data, which was the GDP by individual NAICS 2 categories for the 574 census subdivisions that make up the province of Ontario. So, this was our available data universe in order to build a machine learning. The learner, I'm not going to speak a lot about the GBM because of the lack of time, and both Rick and Kyle have already done a fabulous job. But just like simply put, when you build a gradient boosting machine, you are using the power of the breadth, which means you're using many trees to get an answer, and then you're using the power of depth, which is every time you get something wrong, you're boosting that tree further another level in order to improve that prediction accuracy. But they are basically decision trees, and they're extremely powerful. One of the reasons why I chose to use a GBM, actually, I built both a deep neural network and a GBM, but around 3 months into the process, I dropped the deep neural net. And some of the reasons were, the GBMs are far easier to train than a deep neural net. They're also a little bit less computer resource intensive. You can avoid normalization of the variables. Not that it's a big issue, because there are a lot of normalization techniques and most of them are automated, but it's always nice to not have to do something. The GBM is quite suitable for dummy variables where the DNN starts to become very onerous, where you have to develop hot vectors for a dummy. You don't have to do that for a GBM. But one of the best things about the GBM is it has far fewer hyperparameters. So anyone who's built a DNN, you can get stuck in a rabbit hole of hyperparameter tuning, and that's a big advantage for the GBM. It's also quite conceptually similar to decision making in real life. So if you want to picture yourself doing a decision tree to any activity you do in a day, it's a lot easier to understand that. And it's also got the ability to trace how an observation traverses through the decision tree. So once I was weighing all these options, I said, okay, I'm just going to stay with the GBM now. The deep neural net was a nice experiment. It was producing reasonable accuracy, but it was just getting too painful to keep running two different models at the same time. But talking about that data plumbing, the very first step in this is you need to actually appreciate the data you have, and especially because the data was collected a priori. And there were three things that stood out. The first was, yes, the CVS is great, but unfortunately it has no information on firms, because they never bothered to ask the truck which firm it started from and which firm is it going to. They only mapped it down to a lat long, and the lat long is tagged to the road network. So you can have a plaza, and in the plaza you can have 10 firms, but you wouldn't know where that truck is going to which one of those 10 firms. There are 42 different SCTG2 classes, which what I call the curse of dimensionality. So if you all recall, both Rick and Kyle were showing you all confusion matrices on our 10 classification problem, which is 10 by 10. That's a 100-cell confusion matrix. If you have 42 different SCTG2 classes, you're now looking at a 1,764-cell matrix. And finally, when you have so many classes, you're bound to run into this issue of imbalance. That means you can have certain classes which just have 15 observations, and then you can have some that have like 500. And it becomes quite difficult to get it right for those 15, because the model will get it right for the 500 and it'll think it's doing a great job. So after I'd appreciated this problem with the data, the first thing was to figure out how do you now attach firms to this? Because without the firms, you have very, very limited information to build a machine learner. And because I cannot deterministically assign a firm, I had to probabilistically assign a firm. So for folks who are familiar with the Gaussian kernel, like essentially the algorithm that we developed was, we said, okay, we'll take every truck stop that is tagged in the CVS. We will assign a buffer to that truck stop, which will vary by an urban or a non-urban area. You will then tag all the firms by the various snakes that belong in that buffer. We will fit a Gaussian to the truck stop, and the Gaussian kernel is right here. And we will basically calculate a similarity measure of every firm to that truck stop. So a firm with a higher similarity measure will have a higher probability that the truck started or ended from that firm. And this buffer, it varies, and the way the algorithm was written, as you can imagine, there are a lot of variables that can be influencing this, like the buffer size, the beta coefficient, which is going to decide on the spread of the Gaussian, and at the same time, how far are you going to keep building this buffer till you reach a certain statistical significance in terms of the number of points inside the buffer before you decide to stop it. But regardless, this is the approach we took, and so it turned out to be a very probabilistic approach. But that was the only thing we could do, given that we don't have any information on what firm the truck started from. So this was a big benefit, because as soon as we assigned this, we basically theoretically were able to add 42 different variables to every truck stop. because there are 42 different SCTG2 classes, and there is theoretically we can have a non-zero entry for now 42 different columns, and those entries are all going to vary between 0 and 1 because they are a probability. So once we got the firms assigned, we said, okay, the next problem we had was that because we did it in that synthetic, like, where we went and assigned it probabilistically, there were a whole bunch of cases where, we saw that there were significant outliers. And at the same time, we had yet not overcome the issue of the imbalance in the SCTG2 classes. So, and I know Rick said that he didn't have a great experience with Smort, but I like Smort for its simplicity and for how beautifully conceptual it is, like in order to appreciate how it works. And so what I did was I used Smort to replace the outliers. So the first thing was, let's go and find out for every point and for every variable, we are evaluating how similar it is from all its other points that lie in that same category. And when it is a significant outlier, that means that it lies beyond a certain band, then we go and we actually compute a new value for that using Smort. So if you were to look at it, these big hollow red circles are your actual observations, and Smort uses k-means clustering or your k nearest neighbor in order to impute new values, which are these smaller red circles that are going to lie on a vector if you were to connect these. So we use Smort to then replace outliers. And once these outliers were replaced, Smort was also used to create new synthetic observations for the significantly imbalanced classes. And once again, it uses the same method. And as you can appreciate, once you're using Smort, now you've added more variability in your input data because your values will depend upon whether you're using 3 nearest neighbors, 4 nearest neighbors, 6 nearest neighbors, and so on. But nonetheless, Smort seems to be the sort of industry standard, and it seemed to work reasonably well, and it was far easier to implement than anything else. But that was on the data verification side. There was yet this curse of dimensionality that was bothering me, and we actually, when we started it, we did try to classify all different 42 SCTG2 categories, and it was a real nightmare because it's a lot easier to classify a cat versus a house. But it's not easy to classify a leopard versus a cheetah versus a tiger, because now you start seeing, you need a lot more observations and you need a very rich data set in order to create those differentiations. And when you're using 42 different SCTG2 categories, you are basically in the world of trying to classify a cat versus, like a cheetah versus a leopard versus a jaguar. So, there are just too much of overlap. So in order to overcome this overlap and to also reduce this imbalance, after some time, we decided that maybe we should just focus on the CFAF categories, and we take the top 11 CFAF categories that are in the data set. And you'll see that you start seeing a lot more balance in the observations, although miscellaneous yet stands out as being the highest. So once this was done, we moved into feature extraction. This is a sort of a thing where a lot of people have a lot of preference in how they do it. So PCA, as most of you will know, is the principal component analysis. I first started with PCA, but I soon realized that PCA is very linear, and what we are dealing in is an extremely non-linear problem. So I quickly dropped PCA. Then I looked at TSNE, which is the T student. I'm forgetting what the N and the E stand for. This was an option. I toyed around with it, but then I thought, what? I'm already doing a GBM. I'm going to let the GBM decide on the importance of every feature. And then as some features are just not critical enough, we will just drop them off, in order to avoid overfitting. So finally, I let the GBM do it, and it ran through hours and hours of computer runtime and evaluation. But ultimately, the final feature, the final training data set is what I'm showing in this table. So we had the CFAF group, the tour length, the ln of the tour length was used, the weekday flag, the CSD that the tour starts from, the CSD that it ends in. Then here were all the probabilistic NAICS values. There were the employment values for every buffer in that, for every buffer around a stop. Then we also tagged the GDP, both the first and the last GDP, and the first CSD population and the last CSD population. So all these seem to, like the GBM said, that all these features seem to be relevant and they seem to be important. So as you can see, it's a pretty extensive. There are about 56 different variables that were used. In terms of the final GBM structure, there was a lot of iteration, but ultimately the training data, and we have taken out all the empty truck tours here. There were 25,188 tours, and I think about 80,000 odd stops, truck stops within those tours. There were 6,303 tours were set aside for validation, or like this is where all the models were evaluated in terms of the accuracy. There were 11 CFAF groups. There were 5 K-folds. 250 different trees were evaluated. Then the row sampling rate and the column sampling rate and so on. They're all listed here. And then the hyperparameter tuning was conducted on the number of trees and the sampling rates, the max depth, number of bins, and the number of categorical bins. So it was, I think it took about 2.5 or, I would say about 3 months actually to get to a final GBM structure, which is what you're seeing over here. And there was a whole numerous discussions, arguments, and how do you, like, it's not good enough to just train the model, but how do you even calibrate a model like that? How do you understand its performance, not at the broad level, but by an individual geography, by a distance band? All of that was evaluated and tested. So in terms of GBM performance, I'm showing you the confusion matrix and the accuracy of a confusion matrix. So like, what you see in the books are confusion matrices where generally diagonals are, all the non-diagonals are 0. But the reality is that, that sort of a model is, it's very rare to get that sort of a data set, where you can cleanly slice and have every group cleanly classified. What you generally would see when you're going into large, like too many classes, is a confusion matrix like that. Our overall accuracy was, if you summed up all the diagonals and you divided it by the total tours that were used for the testing, so it was about 39%. So it wasn't something you would open a champagne bottle to, but it wasn't poor if you compared it to if we had just done a Monte Carlo or our accuracy by random chance, which is if we took the distribution in the data by the CFAF classes and we just randomly sampled it, our accuracy would have been 12.2%. So the GBM showed like a 3 times bigger accuracy. So that was a very favorable outcome. Not surprisingly, the miscellaneous category is often confused with a lot of the other CFAF groups. This is also because the miscellaneous had the most number of observations even after all the balancing. But I think one of the primary reasons was that using that probabilistic technique to assign a firm or the probability of any firm from where that truck tour started, what that resulted in was a lot of overlap in the feature space. So we weren't able to clearly identify that only certain NAICS2 categories will have a very high probability of a miscellaneous truck tour. Those probabilities were spread across all the NAICS2 categories. And also, I think part of this goes back to the way the survey was done, because what the survey says, or it asks the trucker, is which is your primary commodity group that you're carrying, And if the surveyor cannot identify that, or the trucker cannot, then they just classify it under miscellaneous. So, that results in a lot of bleeding in the space. But 39% wasn't too bad, considering from where we started and the fact that a random model would have produced 12.2% accuracy. But this is at the aggregate level. It's not always good to just look at the model like that. So then what we did was we said, okay, let's look at the model by the GBM's performance by the truck tour origin. So we took all the census divisions where the trucks are starting from. And on the Y scale, we are plotting their accuracy from the GBM. That means, if the GBM predicted, like in this case, in the Algoma census division, there were 34 different CVS truck tours that started in our testing data set, and our accuracy was around 51%. So, we were able to get it right 51% of the time. And we actually plotted that because this was going to be used to identify where the model has some biases and where we can potentially go and do some more surveys. And at the same time, for example, if Peel, which is a very critical geography, where we have 966 surveys, the model was only getting about a 38% accuracy. There was a lot of discussion whether we focus our efforts on improving the accuracy here by actually weighting those observations a lot more, or creating more synthetic observations for that geography. Ultimately, we didn't do that because this was the very first generation of this model. But in this round that we are about to embark with them in the next 3 months, we might go back and look at whether you can improve the performance specifically for certain geographies. Then we also looked at the GBM's performance by distance bins, because this is quite critical for the CVS survey. And these, so the data or the tours are binned into every 100 kilometers. And as you'll see that for the really long tours, it was very easy for the GBM to get it right, although there was just one observation in that, but it got it right. And that's why your accuracy is 1. And this is also easier to appreciate because there are only certain types of commodities that are going to get carried by these really long distance truck tours. So the model can actually classify that much more easily. But in the really short distance tour bands, which is, let's say, from the 100 to 500, you will see that the accuracy fluctuates between 39 and around 50%, because you have a lot of different commodities, and the miscellaneous groups are quite, they're quite prevalent in this in these distance bins. But yeah, like overall, the client was reasonably happy. Unlike Rick's client, who was quite hard-nosed about accuracy, our client was a little bit more lenient, and they could appreciate the problem we are dealing with, and also the fact that we are synthesizing the input data, which is not very, which is not highly recommended, because you don't want to have to synthesize input data. You want the input data to be as is what is given. Finally, some reflections, because as I said, hindsight is 2020. If I had to do this again, I would do it quite differently, at least a few things. But some of the questions that I have noodled over the last couple of years while I have presented this work and also thought about its application is that should I have spent some more time on testing and creating the Gaussian parameters for generating the firm probabilities? Absolutely yes, but it was a significant non-linear problem. As you can imagine, there are 5 or 6 different variables that can be adjusted, and for every adjusted variable, you would need to run a whole series of GBMs, and that requires a ton of computing resources that were just not available. Then the other question that came up in my mind was that can we focus on significant geographies and OD pairs and calibrate these models? And the short answer to that is yes. And this is a really exciting development even for more choice and auto ownership, where you can now start to calibrate. Even after you've built a machine learner, you can actually calibrate certain segments of the population better in the event they are of significant interest. And the way we would calibrate this is, where we would weight those geographies much higher than the others. So if the GBM gets those geographies wrong, the loss function is actually penalized quite substantially. The question that Rick kept asking me all along this entire process was that, can patterns learned on a smallish data set be deployed in a true ML environment? And my answer was that this is a start. As we collect more surveys, this data set is going to expand, and we'll be able to eliminate any biases that we see. So yes, you can apply it, but yes, you have to also recognize that small data sets have significant biases in some cases, and you need to appreciate, or you need to address those before you can claim victory in this. This was a burning question, was number 4, that why can't we just go and collect which firm the truck originates from and is destined to? And MTO in their new round of surveys is doing just that. So we can either eliminate that entire Gaussian kernel, or the more interesting aspect for me is that we can now train that Gaussian kernel using the new information we are going to get from these surveys. And I find that quite actually interesting if we could do that. And finally, the question is that, can we optimize our next round of survey collection based on what we've learned from the GBM? And once again, it's absolutely yes, we can, because as I showed you all, there are certain geographies that we are not doing very well, and those could be because we just don't have enough data in them, or if we have enough data, it's just not got the right spatial accuracy. So now MTO is using this information to try to figure out that maybe they need to go and get better information in Toronto, because it's got 408 observations but only 38% accuracy. So that sort of optimization of the surveys can take place. With that, that's about it. Over to you all for any questions, comments.
All right, you've definitely got some questions. Let's see. So Elizabeth asked one about measures of accuracy, and she says, I'm wondering if there are good measures of accuracy, recognizing that the difference between some results are not as important as others, i.e. green and aqua versus green and red. Likewise, are there methods that recognize similarities in estimation?
Actually, that's a really good question, Elizabeth. And I'll give you the easier answer, which is on the second part. There are probably 15 or 20 different measures of similarity out there that one can use, from Kullback-Leibler divergence. Like in fact, there's a Jacquard distance and so on, and the one that we generally use in our trip distribution models, it's like I'm just blanking out on the name, but either Rick or Kyle can help me here. But we always use that to understand the difference between a trip distribution. So there are a lot of these measures. I generally use Kullback-Leibler, but there is one challenge with any similarity measure. You want to make sure that your similarity measure is symmetrical, which means if you're measuring it from between A to B, it should have the same answer when you're measuring it between B to A. And the Kullback-Leibler does not have that in its raw form, but once you tweak it, you can actually use that measure. There is a very simple tweak that is done for the Kullback-Leibler, and yes, it can be used. And that's my go-to measure. And of course, then there is the very venerable, standard variance norm, which is an L1 measure, or an absolute difference between two distributions, which is then divided by 2 to ensure that it stays between 0 and 1. Whether we used it here, no, you cannot, because the true, like the actual confusion matrix should only have entries on the diagonal, right? So you don't really need to look at a similarity measure here. In terms of accuracy, this is a fairly debatable point. This simple accuracy measure, of course, is not very accurate, or it's not very appropriate to just say 39% accuracy. That's why I like to see what's the random chance. And there's also some other accuracy measures, like they're called the F2 scores and so on, that can be used. But it leaves a lot for the analyst to interpret. Because, for example, if the score is always between 0 and 1, at what point do you decide that your model is good? You know, like, is a score of 0.5 and above good? If that's the case, then what about a score of 0.499? You know, so you always have those cliff effects. So it's a little bit of an art.
So yeah, to that, I will add, if you think back to the income imputation problem, if you go back and look at that code, you'll see that I'm choosing an ordered cost function, which is how it knew, right? Just like an ordinal regression, that's how it knew that, you know, 3 is closer to 4. It's not just a label like A, B, C. They actually, it'd be better if the right answer is 5, it'd be better to be 4 than 10, for instance. So sometimes I think there are probably more measures of accuracy and cost functions than there are learners. So it can be really overwhelming, but there's precision and recall and F1 scores and kappa and just an enormous amount of measures. But the short answer is yes, you can tell it, you know, these things are ordered, and it'd be better if it's green, it'd be better to choose aqua than red. All right, I'm going to scroll up a little. So Elizabeth asked, kind of on the admin side, and Mossam, I'll give this to you. Feel free to give it to Rick or me, but she asked, you know, how much does it cost to do something in machine learning versus traditional? Where traditional works, and you could pick, you know, something like regression or ML.
Sorry, Kyle, can you repeat the question? You know, my audio just cut
Sure.
out.
Oh yeah, sure. So, you know, what's the cost of doing machine learning to solve a problem compared to like a traditional regression or logistic regression or something like that?
Oh, okay. Well, it depends, Elizabeth, where you are in the machine learning curve, right? Like if you're just starting in machine learning, yes, it's a lot more that you have to invest. But if you've done already a few, plumbing one up is, you know, it's not really a big lift at all, because the data exploration, all of that is common to even a much more traditional statistical or econometric technique. Without that, you know, it would be a mistake to build any model, like, you know, even a simple linear regression model. And that's, I believe, 80% of the work. The last 20%, you know, for folks who've already built, you know, machine learners before and they know their problems, like to me, it's a lot easier to build those than it is to, or it's at the same level than building a linear regression or a logit model.
I would definitely echo that, right? The data prep, we already do that, right? We already spend a week processing household surveys or whatever. And once the data is processed and ready, in fact, if you're using like the MLR package or the H2O, it's just changing one variable and it will do decision tree or regression. So yeah, like Rick said, that small box of ML, it's a tiny box, and that's kind of the difference. So once you're comfortable in both, they're interchangeable.
Yeah,
Rick,
I
did you want
would
to add
agree.
anything to that?
Yeah, I think we often shortcut the data munging and cleaning and exploration when we're doing traditional models, or we go back and find things when we get stupid model outputs. But in machine learning, you cannot shortcut the 80% data learning load. In general, neural networks take a long time to train, whereas most of the rest of the machine learning stuff goes, you know, pretty doggone fast. But even if it takes a week to train a neural network, it does predictions in a matter of minutes. It can rip through 500,000 predictions in just a couple of minutes. So the prediction, once you built an ML stack, is pretty fast. In my particular example, it took a good 3 months for some decently smart people to come up with a model estimation for the logit model that looked pretty decent. We did everything I showed you in 2 weeks on the machine learning side. No, that's not true. It took another week to write the implementation code that stitches it into the model and does the polling and everything else like that. But it literally is weeks versus months.
All right, we've got some questions. Let's see. Sam asks, what methods you use to uncover the unobserved variables or factors that represent the common variability across observed variables? I might have to read that question again. So basically, you know, how would you uncover unobserved variables or factors? Sam, if I'm butchering your question,
Oh, okay.
if that makes sense, please respond to it.
Okay, now I'm reading it now. So what methods do you use to uncover the unobserved variables or factors that represent the common variability across observed variables? Oh, I see. Okay, so let me try to just visualize this. So what you want to know is there are certain variables or factors across those classes that have a common variability across observed variables. Sam, I got to apologize. I haven't quite, I feel like I've understood your question, but I don't think I have. So you want to rephrase it, please?
And feel free to unmute yourself.
Oh, yeah.
If I guess at what he's saying, he's saying what machine learning methods are out there that will allow you to deduce what variables or factors are missing in the data.
Oh, okay, I see. Well, I'll tell you for short, not in supervised learning, you don't have that. And I think Rick probably already covered this last Tuesday, that all the methods that we have out here are supervised learning. So whatever data we are giving it is what it's trying to deduce it from. If we know of some missing data, you know, that's up to us. It's not really, at least in my experience, a GBM or a deep neural net cannot point you to that direction. Now, however, if you were working in a completely unsupervised environment, and actually even beyond unsupervised, if you were working in a reinforcement learning environment, yes, there is a theoretical possibility that it will generate for you, or it will point you to a direction where you have a gap in your data. Because as you start to segment your data and you start to evaluate its performance by the performance of your model by various segments, and let's say one of your segments is income, you know, you might start to find that you do not have enough information on certain income categories. And, you know, that can, it can help you, but it can't do it automatically. Unless I misunderstood your question, but that's my,
Okay.
that's my answer.
So I know we're,
and to pile on to that, I think that this is where we have to do the thinking. The machine is not going to be creative about problem solving or second guess why we didn't put in the data we did. We need to learn from it in order to better pose the data to these learners. Maybe someday AI will be able to do this on its own, go out and look at different other sort of things and found where it found associations between variables that we didn't include in our data set, et cetera. But I don't really think I can think of a great ML way to isolate that stuff. Now, the fact that it doesn't give us very good clues is, I think, our biggest challenge. And I think we are making progress in being able to better uncover some of the hints that this thing is giving us. But we just, most of us don't have enough experience with ML yet to do that.
So, Rick, Elizabeth asks like a broad ML question. She says, given the potential for applicability across a wide variety of problems in the travel analysis field, should we be giving equal or more weight to ML methods in a traditional transportation master's degree program? If so, what class or techniques would you sacrifice to make room for it?
Wow.
My pavement condition class could probably go.
Yeah, but there's a lot of traditionalists that would say that you need to understand the broader realm.
Yeah.
Nothing I've learned in machine learning is, except for deep neural nets, is not directly applicable to learning how to build better models in general. And when I think of all the statistical methods that are under the hood there, we've tried most of them in our regular lives. So I don't know that it's that big of an extension to go from a discrete choice model to go on to machine learning. But can you cram all of that into a master's program? I don't know. Maybe I think that what you should be doing is grabbing people who have an undergraduate degree in data science with some exposure to machine learning and deep neural nets and train them in transport planning. People that have an interest in doing great things for social causes from a data science background. Because for the stuff we're doing, I mean, I would argue, I are an engineer, but the civil engineering undergraduate degree doesn't, except for its background in probability and statistics, doesn't really prevent a lot of people from doing great things in travel demand forecasting. You don't really need that. I think the way things are changing with big data, it's more data science, baby.
All right.
Didn't answer her question, but I got around it.
Yeah. Well done. That looks like all of our questions. Wait, let's see. David just makes a comment that traditional methods, the frequentists group, have kind of reached the end of their lifetime. So why not use ML instead and embrace the Bayes? I gotcha. That's more of a comment.
I totally agree with that.
Yeah.
I'm totally with David on that.
So
well,
in that case, given our time, that I know that we're over, maybe I'd kick it back to Elizabeth to close us out, or to Rick.
Well, I think we send it back to Elizabeth. We've all done all the damage we can.
Sure. Well, I'll just thank you guys, the three of you, for giving us all a lot to think about and introducing this topic. And I would encourage everybody to keep the questions coming. Either you can join our Slack group, or you can email us, and we can try and answer those questions. We're going to put up the video and the presentations, maybe edit out some comments, who knows, on the website on the event page, and that should be up there. And I think that our next session is in July. I can't remember the exact day, but it's about equity in data collection and modeling. It should be a great session. We have some great presenters and a great panel about that as well, which of course is an important topic in machine learning as well. And please fill out the survey. There'll be a link in the follow-up email. Please fill it out so that we know what you think and we can improve for future learning sessions. And I think that's it. Thank you, everybody.
Thanks, guys.
thank you all. Bye.
Thanks so much. Bye-bye.